Hi, my name is Todd Signetti. I'm a principal product manager at AWS. And with me today, I have Ram Ramani, who's a security solutions architect. Today, we're going to talk about AWS Certificate Manager, Private CA, and the subject is creating and managing root and subordinate certificate authorities. We'll talk about some of the challenges of operating a PKI, and then we'll talk about ACM Private CA and the root CA hierarchies features that allow you to operate an entire public key infrastructure. And then we'll show some use cases. We'll do a demonstration of creating a root CA and a subordinate and issuing trusted certificates. And then we'll really dig into some of the planning and best practices that are important to consider when you create a root CA hierarchy. When we launched ACM about 3.5 years ago, customers told us that they had challenges with managing certificates. Certificates expire, and when they expire, they need to be deployed and bound again to their endpoints. And this is the problem that ACM solves. It makes it easy to manage and deploy public certificates on AWS infrastructure. At the same time, we talked to them about the problem of certificate management. Customers also told us about the problem they had in the same space, which was operating a CA was challenging. And many of these customers viewed operating a CA infrastructure as undifferentiated heavy lifting that took away from their focus of operating their business, and they wanted AWS to manage this infrastructure. So we launched ACM Private CA. ACM Private CA is a managed private CA service without the upfront investment and ongoing maintenance costs of operating your own private CA. With ACM Private CA, there's no need to build your own CA infrastructure. It's a managed service. It's secure and backed by FIPS 140-2 Level 3 HSMs for operating on the CA private keys. And so there's no need to manage your own HSMs. ACM Private CA has access controls, auditing, and logging built in, and you can control the administrative policies for the CA without operating the infrastructure yourself. You can automate certificate creation and distribution with APIs and deploy private certificates programmatically. You can also use the certificate manager to centrally manage public and private certificates from one place. With subordinate CAs, you could chain your private CA up to an existing root or parent CA in your existing infrastructure. In June of this year, 2019, we launched root CA hierarchies for ACM Private CA. This is a new feature that allows CA administrators to use ACM Private CA to create a complete CA hierarchy, including online root and subordinate CAs, with no need for external CAs. ACM Private CA also allows a hybrid hierarchy with offline and online CAs. And a CA hierarchy essentially provides strong security and restrictive access controls for the most trusted root CA at the top of the trust chain, while allowing more permissive access and bulk certificate issuance for subordinate CAs lower in the chain. You can create and secure a highly available CA infrastructure without building and maintaining your own on-premises CA infrastructure. And this diagram shows the process of generating a certificate signing request and taking it to an intermediate CA in your existing CA infrastructure. So prior to root CA hierarchies, this existing CA infrastructure was a required component that you had to have and you had to operate. You could issue end entity certificates to identify resources like TLS endpoints or IoT devices that are trusted in your environment because the root CA is distributed to the trust source in your environment. Customers like this ability, and they viewed it as a supplement to their existing CA infrastructure, but they wanted AWS to do more. And so this is why we introduced ACM Private CA hierarchies. You can see in this diagram, it's a similar diagram, But in this case, AWS is managing the entire infrastructure for you. It's hosting a root, an intermediate, and an issuing CA. And the process of trusting or adding an issuing CA to the hierarchy is very similar. The CA, you create the CA, you issue a certificate signing request for that private key for the issuing CA, sign it with the intermediate CA, and then import the signed certificate. But now, instead of requiring an external root and intermediate CA, that's optional, and AWS can host the entire hierarchy. We'll show you how to create a two-level CA hierarchy in a demo coming up. Ram will show that. And first, though, I want to talk about some of the organization and use cases for private CA. So the first question is, why create a CA hierarchy at all? This is a common structure across time where people have, administrators have organized CAs this way. But the question is, why is this a common organizational structure? And the primary reason is that it allows you to restrict access to the root CA, to protect the root against misissuance, because the root can issue CA certificates, which can then in turn be used to issue end entity certs. And we want to provide the strongest levels of access controls, isolation, and protection for that root CA, because it is really the root of trust in the environment for identifying resources in your environment. At the same time, we want to grant more permissive access to subordinate CAs. Subordinate CAs are really the workhorses of the PKI world. They're the CAs that issue certificates in bulk. They're the ones that we provide access to developers or others that are trusted, but we want to have strong access controls, but we need them to be available and accessible so that they can be used to issue certificates that identify resources. Another reason is that we want to delegate subordinate CAs for different applications or groups. So one group may have a CA for a dedicated purpose for issuing TLS endpoint certificates to identify servers. Another CA may be used specifically to identify IoT devices. And these may be under different administrators, and we want each administrator to be able to control the policies around their CA. And delegation and a hierarchy allows them to do that. The next reason for having CA hierarchies is to provide auditing and alarms that can be specific to the CA or to the level of the CA hierarchy. So for example, the root CA, we want to have careful monitoring, we want to have alarms and notifications for issuance from a root CA, because the root CA is really typically used infrequently and only to issue certificates for subordinate CAs. So when there's an event, an issuance by the root, that's a significant event that we want to know about, and that should only happen under very controlled circumstances. And so having alarms and auditing very carefully for the root CA makes a lot of sense. For the subordinate CAs that issue thousands or hundreds of thousands of certificates, it doesn't make as much sense, and it's not efficient use of time to audit every single certificate. We certainly can't generate an alarm or a notification for every one we issue. So we want to do random sampling of subordinate CAs, but not the same level of auditing that we would do for a root. And there is one case that is not really common, but a valid use case of not using a hierarchy and simply issuing certificates directly from the root CA. And this isn't something I would typically recommend, but for one use case, and that one use case is where you already have a root CA that you've created and you're issuing certificates directly from it. And maybe you're using something like OpenSSL, where the root key is stored on a disk. And in this case, it really is a better solution to move to an HSM-backed solution like ACM Private CA, where you get the benefit of the HSM and the managed service without, in that simple case where you just want to issue certificates directly from the root, you can do that with ACM Private CA. There are some downsides to that approach, which is that if you want to revoke the root CA, there's really no way to revoke a root CA. The only way to do it is to remove it from your trust stores. So if you don't have a subordinate CA and you have an incident where you need to revoke the root, the only way to do it is to pull it from the trust stores. A hierarchy gives you the ability to, potentially revoke a subordinate issuing CA rather than revoking the root, which can be less disruptive operationally. The next question is, what can end entity certificates identify? So with ACM Private CA, you can use certificates to identify TLS endpoints and resources, things like websites, databases, or other TLS server endpoints, servers, instances, containers, or other resources in your cloud environment or on premises that use TLS, so clients or servers. Next is IPSec VPN endpoints. And IPSec VPN is still used to provide an additional layer of security on top of TLS, so defense in depth for using both TLS and IPSec VPN, or in some cases, it's used by itself to bridge across an untrusted network using encryption and secure authentication and identity. Next is dynamic identifying cloud resources that are created dynamically through automation. Things like auto-scaling, CloudFormation, or your own automation that ACM Private CA supports through APIs and SDKs. You can use these APIs to create certificates that identify resources that are created dynamically and include that as part of your automation to identify private resources. And finally, IoT devices, things like one example is Alexa for Business used ACM Private CA, and there's a public blog post that describes the application in more detail. But what they're doing is giving a certificate to Amazon Echo devices so that they can identify themselves on enterprise WPA2 Wi-Fi networks. And there's lots of applications where private certificates are used to identify IoT endpoints that are connecting back to a back end or connecting to other resources, and that certificate provides identity for that device. There are a few other enrollment protocols that we're considering for future uses where ACM Private CA doesn't fit well today. And those are things like ADCS, Active Directory Certificate Services auto enrollment, where you have users and machines that automatically get certificates through Active Directory using ADCS. ACM Private CA doesn't support the templates required for that application today, but again, it's something we're thinking about for the future. And second, mobile devices using SCEP, Simple Certificate Enrollment Protocol. And in the case of SCEP, ACM Private CA can provide the certificate authority component, but not the registration authority component. But we're definitely looking at opportunities to integrate with enterprise mobile device management, MDM solutions, to give you the ability to issue certificates to identify devices in something we're looking at in the future. Some of the use cases that ACM Private CA can be used for, and places where ACM Private CA fits and can replace an existing solution, are to replace existing HSM-backed online root CAs or intermediate or subordinate CAs. This is a great case where you have an HSM. It's probably challenging to manage and operate and keep it up to date. You can use ACM Private CA to replace that with also HSM-backed CA, but AWS takes care of managing the infrastructure. Another use case is to replace software or server-based CAs where you don't have an HSM. Your key is stored on disk or in memory. A great example of this I see all the time is to replace OpenSSL CAs, root CAs that are storing their keys on the disk. Generally just not a good idea, but ACM Private CA gives you an alternative to that. Another option is to replace offline root CAs. And this isn't something for everyone. If you have an offline root CA and you're happy with it, I would tell you for security purposes, keep using the offline root. But if you're not happy with some of the parameters around operating an offline root, ACM Private CA does provide an alternative with an online root. And we'll talk about the pros and cons and factors to consider later. Another application is to complement an existing root CA. For example, you can create a root CA in a hierarchy for cloud resources. And it really you would limit the distribution of that root CA to specific hosts, for example, just your cloud resources. And that really allows you to constrain the trust boundary to a subset of your environment. So you can have a cloud environment that is set up to trust certificates from a particular root CA, and that can be a different root CA than you use for on-premises. And that really allows you to get started quickly to include the root CA in the trust stores of just a subset of all of your environment with a separate root and trust chain for on-prem CAs. And examples of this are to create a dev, test, and production environment on AWS with the same infrastructure and APIs shared across dev, test, and production, so that when you issue a certificate, the same way that you issue it in production will be the way that you've developed in dev and test environment. So you know that there's no differences. And a common goal you want your developers want is to have a common environment across dev, test, and production, so that when they test it in their test environment, they know it's going to work in production because it's the same. And really, the goal of this is to allow developers to go faster by automating certificates and certificate management and allowing them to build this automation with private CA APIs. Next, we're going to have Ram Ramani show how to create a CA hierarchy with a root and a subordinate CA in just a few minutes.
Hello, everyone. We're going to show you a demonstration of ACM Private CA and use this diagram as the architecture. So in this architecture, there is an application load balancer, which is backed by a Lambda function. And the Lambda function supplies HTML code back to the application load balancer. The goal is to establish a secure TLS connection between this Firefox browser and the ALB. And the Firefox browser is going to hit this domain acmdemo.com, this private domain. And the certificate for this private domain is going to come from the ACM service. The CA hierarchy that we will use for this demo is going to be having two levels. One is the root CA and then the subordinate CA. The subordinate CA will issue an entity certificate that will go on the application load balancer. This is only one application of using a private certificate and for hitting a private website, but there are many others. So let's take a look at how this works. So I'm going to go to the AWS console under the AWS Certificate Manager service and click on Get Started under Private Certificate Authority. You have two options, either to create a root CA or a subordinate CA. We'll start with creating a root CA. Click Next, and then organization will type in as my company, leave the rest of the fields as blank, and the common name, say my company root CA generation 1. You can have multiple certificates of different generations, but in this, so this is the first one, I'm going to call it G1 or generation 1. And the certificate key algorithm is going to be RSA 2048. We will not enable CRL distribution for this demo. No tags as of now. And for configuring CA permissions or authorizing or denying ACM permissions to renew private subscriber certificates, we will deny it because we're not going to issue an entity certificates using the root CA. Click next, and then make sure all the information is accurate. So you can see here that the information is as I typed it. If you want to change it, you can always change by editing it by clicking right here on this icon. So click to confirm that you understand that you'll be charged a monthly fee, and then confirm and create. So at this point, the root CA key pair has been created, and we'll click on Get Started to take the root CA CSR and sign it by the root CA's private key. Think of it as a self-signing mechanism. We'll set the validity to 10 years and the signature algorithm as SHA-256 with RSA. There are others if you choose to do so. Click Next, and then confirm and install. It takes about 2 to 3 seconds, and after which you will see on the console that there is an active root CA with the common name that we created, my company root CA G1. The next step for us is to create a subordinate CA. So click on Create CA, select Subordinate CA, and then we'll keep the same organization name, leave the other fields as blank, and the common name is going to be my company subordinate CA, again, generation 1. Click Next. The certificate authority key algorithm RSA 2048. We will not enable CRL distribution for this demo. No tags. And in this case, I'm going to authorize ACM to use the CA for renewals because we're going to issue end entity certificates with this subordinate CA. Click Next. Make sure all the information is accurate. It looks good. And then click to confirm that you understand the pricing model, and confirm and create. So the next step is to install this CA certificate to activate your subordinate CA. Let's get started. There are two options. One is you can either select the root CA that you actually own, and you can bring that in, or you can use the root CA that you just created within the ACM PCA service. So we will go with the option where we will, the first option, ACM Private CA. Click Next, select the root CA that we just created with the common name, my company root CA G1. Let's set the validity to 3 years, and the signature algorithm is SHA-256 with RSA. And you see this parameter here called path length. The path length, you have 4 options. 0, you can set it to 0, 1, 2, or 3. We're going to set it as 0. Setting the path length to 0 means that this subordinate CA can issue only end entity certificates and not CA certificates. This is a security best practice to ensure that the subordinate CA is issuing cannot issue a CA certificate. So let's click Next, and then click Generate. So there you can see now that there is a subordinate CA with the common name, my company subordinate CA G1. So next step for us is to go to the certificate manager and create a private certificate. So I'm going to request a private certificate and select the subordinate CA that we just created. And the domain, I'm going to put it as alb.acmdemo.com. Review and request. Confirm that the domain looks good and the CA is the subordinate CA, and confirm and request. So it takes about 2 to 3 seconds, and you're going to have a private certificate for the domain alb.acmdemo.com. So there you go. The certificate is issued and ready to go. So let's now go to the EC2 service and find the load balancer on which we can put the private certificate. So just to let you know, this architecture that I showed earlier, this is pre-created. The ALB and the Lambda functions have been pre-created using a CloudFormation template. So we're not going to create it manually during this demonstration. So let me go back here, go to the load balancer section, and you will see that there is a load balancer that has been pre-created. Let's go to the listeners, and I'm going to add an HTTPS listener. So the HTTPS listener will be listening on port 443. The default action is going to be forward to the Lambda origin, which is going to give the HTML code back to the ALB. And for the certificate, I'm going to select the certificate for the private domain that we just created and click Save. So at this point, the certificate has been applied to the ALB. So the next step for us is we're going to go and try to hit this private domain. Let's see what happens. So it says that the connection is not secure. The reason is that the root CA certificate is not available in the Firefox browser's trust store, and hence Firefox cannot trust this website. So the goal for us is to next put the root CA certificate inside the trust store of the Firefox browser. So I'm going to do this really quickly. So let me go back to the certificate manager service. And I'm going to go pick up the root CA certificate. So let me select the root CA and go to the CA certificate. And I'm going to download this certificate body to a file. All right. So this is called certificate.pem. So there you go. So this file, and I'm going to go to Firefox Preferences and import the certificate.pem. So let's go here. I'm going to do this quickly. Typically, in your organization, you would be using automation for importing root certificates into your trust store. I'm just doing this manually here. There you go. Okay. So at this point, I have actually added the root CA certificate into the trust store. So next, the goal for us is to see whether now the certificate is trusted and we are able to establish a secure connection with the ALB, and the Lambda code HTML is relayed back to the browser. So let's take a look. There you go. So you can see here that there's a trusted lock icon, and this private domain is trusted by the browser, which means that the private certificate is valid and trusted. And you can see the hello world has been given back by the Lambda function and relayed all the way back to the Firefox browser. So we were able to create a private certificate authority hierarchy and then issue an end entity certificate, and then go back to the application load balancer and put that end entity certificate and make it trusted by the Firefox browser. Thank you. This is what I wanted to show you. Thanks.
Thank you, Ram, for the demonstration. As Ram showed, it's pretty easy to create a CA hierarchy. And we want to be thoughtful, however, about how we create a CA hierarchy, because as we know, the PKI infrastructure can last a long time. And so we want to be really thoughtful and plan our CA infrastructure so that we're creating an infrastructure that's going to last and we're not going to have to go back and redo things. So some of the things to think about when you create a CA, and Ram showed a few of these things. I'll talk more about them in depth. First is key sizes and key types. ACM Private CA supports RSA and elliptic curve with a few different key sizes. So the most common key size is RSA 2048. That's what Ram showed. That has the most trust in the widest range of browsers and operating systems going back to Windows XP and beyond. But some customers now are looking at RSA 4096 for security purposes, those longer keys providing more protection. And elliptic curve algorithms are really taking off in the mobile space where you have limited compute power to operate on those keys. So smaller keys, more compute efficient, but less acceptance in browsers and operating systems. If you have so you have to look at your user base and the clients and decide if those clients support ECDSA. That's certainly a good choice. Next, we want to think about the revocation configuration. Ram didn't show configuring a CRL, but ACM Private CA does support generating CRLs on an ongoing basis and allows and sends them directly to your S3 bucket. You want to make sure that that S3 bucket is reachable from the clients that are going to be checking revocation. And furthermore, we recommend creating a CNAME, which is in DNS terms a canonical name, It's basically a level of indirection. So it's a friendly name that you can give to your CRL URI, and that's what is included in the certificates that you issue, and that's how the client looks up the CRL. Instead of using the bucket name, the C name is a friendly name that the client uses to look up, and it gives you the ability to therefore change the S3 bucket name over time without having to change the C name that you give it. As long as your C name is in DNS and your clients can use it to look up the S3 bucket, then that configuration works. And next, you want to think about turning on CloudTrail logging for your API calls for ACM Private CA. That's just a strong recommendation across the board to turn that on when you start using ACM Private CA, and that gives you the ability to monitor and see what's happening in your environment in terms of what calls are made. You can also go back over time to look and track down what API calls were made. And then CloudWatch Metrics gives you the ability to alarm and generate notifications for specific actions that occur. For example, you can configure monitors for metrics such as successful and failed certificate issuance or CRL generation. A typical application of this is one that I mentioned before. When you have a root CA, you can configure an alarm on successful or failed issuance attempts so that you know when the root CA is being used. And that should really be confined to a ceremony and not happen without your knowledge. Next is audit reporting, thinking about who is going to perform audits, how often are they auditing, and what are they looking for? What is the review process? ACM Private CA allows you to generate an audit report that includes all of the certificates issued by the CA, but you want to think about how you're going to use that and how you're going to monitor. And typically you probably are going to look very carefully at certificates issued by the root CA and only do sampling for certificates issued from subordinates. Next, access policies. You want to think about which users, groups, or roles have access to the CA and what they can do. I'll talk in more depth about and give some examples of access policies. And finally, CA lifecycle management. What will you do when the CA certificate nears its expiration date? Will you create a new CA and issue new certificates from there and phase out the old one, or import a new certificate and continue to use that CA with a new certificate, a new lifetime? General recommendation and best practice is to create a new CA, as Ram talked about, having a next generation G1 and then go to G2, but you have that choice with ACM Private CA. So some best practices, we'll talk about some security, and then this configuring the CA hierarchy, the CA lifetime, and how to choose the validity period, and then some operations that you'll need to take care of. First, I want to talk about offline versus online root CAs. And an offline root CA, as you know, is typically a physical HSM. It's never connected to the network, and it's typically stored in a secure location physically, like a vault. And whether you choose an online or an offline root CA really depends on your requirements and your internal policies. I would say from a security perspective, the best practice is to have an offline root CA. And many customers have offline root CAs. They're going to continue to operate them and maintain them, and that's great from a security perspective. The benefits of an offline root CA is primarily that it's never connected to the network. And so there's no chance of remote access. You have to have physical control of an HSM plus typically multiple security officers to perform an action like issuing a subordinate CA certificate. And so that gives you strong physical security without the chance of remote access. The challenges can be that if you have a remote, geographically distributed team or security officers that don't have the ability to all converge on a single location, that can be challenging. And especially if you have an operational event where you've put off issuing a CA certificate, subordinate CA certificate for too long, and you have an urgent need or even an operational event caused by that certificate expiring, and you need to gather these people together quickly to perform a ceremony. Sometimes those geographical and timing constraints, logistical issues can be a problem. With an online root CA, you have logical access controls and logical isolation instead of physical access controls. It does allow you typically to have faster signing, which can be important if a CA expires or is nearing expiration and you need to quickly create a subordinate CA. And typically with an online root CA, it's easier to manage, it's easier to control the policies without dealing with specifically, understanding the nuances of a physical HSM. And it doesn't require physical presence. And of course, that has pros and cons, as I talked about. So next, let's talk about some of the logical access controls and isolation that you can put in place around a private CA. The first recommendation is to use account separation. So if you have a root CA, keep it in a different AWS account than your subordinate CA or intermediates. And this gives you the ability to have very restrictive access to root and intermediate CAs that are high trust or high in the CA hierarchy. The demonstration that Ram showed actually showed the root and subordinates in the same AWS account, but general recommendation is to separate them. That does have the downside of the demonstration where Ram selected the root CA from the dropdown would not be an option, but it's still a possibility. You can perform those steps. The one step where the root CA signs the CSR, you can do that manually through a CLI or an API call. Next is the access controls that you can use to control access to the ACM Private CA are determined by AWS identity and access management policies. And if you're not familiar with these, it's a very rich language and a set of controls you can put in place to determine which users, groups, or roles can perform which actions. And with the policy language, and I'll give an example in a minute, you really have very granular control over what actions can be taken by which users and on what resources. So to get you started, AWS and specifically ACM provide managed policies that are managed by AWS. They're predefined and they're just automatically in your account. You don't have to use these, but it's a good place to look to get started at some examples. And you can certainly take these and customize them for your own purposes, or just use them if they meet your needs. There are 5 managed policies that ACM Private CA supports. Full access, which is just complete access to all of the APIs. There's a privileged user, which allows the privileged user can create subordinate CA certificates, but not end entity certificates. And there's a user that can only create end entity certificates. And end entity certificates are just those that identify a resource like a TLS endpoint, a web server, or an IoT device. And then there's an auditor role that allows the auditor to create an audit report plus have read-only access. And finally, just straight read-only access. And next, I'll talk about, I'll give you an example of one of those managed policies for the privileged user. But first, I'll talk a little bit more about auditing and logging. Very important in terms of making sure that your logical controls and isolation are working properly. You want to audit and make sure that the access that you think you're granting is what is being enforced, and you don't see any activity that is not authorized. And I mentioned you can create alarms on certificate issuance for root CAs. You can do a careful review of the audit report for roots and sampling for CAs that are lower in the hierarchy, like issuing CAs. And of course, CloudTrail, as I talked about before, is a best practice for monitoring and reviewing the API calls. So let's dig into a managed IAM policy that is included with ACM Private CA. This is the privileged user policy. This is one of the 5 managed policies I talked about. And this language that you see is just JSON, and this is the language of IAM to allow you to control access to resources on AWS. This may be a little intimidating at first, but once you get the hang of it, it's pretty straightforward. So this policy has 2 clauses. There's an allow policy and a deny policy. And so what the allow policy says is to allow issue certificate on this wildcard star asterisk means any certificate authority. And there's a condition here which requires that the template that is used in order to match this clause, the template that's used to issue the certificate has to be a CA certificate template. And that's the template for issuing subordinate or root CA certificates. So what this policy says is allow the user that's assigned this policy to issue certificates that are CA certificates. And then the other clause here on the right side is the deny policy. And it's very similar. The only difference here is that the string, instead of string like, or essentially string matching, the string is not like the template for CA certificates is, and the action is deny. So what this says is, unless this template is a CA template, then deny the issuance. And together these basically say strictly this privileged user can only issue CA certificates and cannot issue end entity certificates. So this is a way to really lock down what this privileged user can do, prevent them from issuing end entity certificates, and only allow them to issue CA certificates like subordinates and root certificates. And you can be even more specific to customize this to say you could have a user or a policy that can only issue root certificates and not subordinate CA certificates. And you can customize these as much as you want. But there's a lot of power and flexibility in the language and being able to specify these. Next, we want to think about the CA hierarchy and where is it appropriate to add another level in the CA hierarchy, and when should we add a level, when should we try not to, and how do we enforce that? So one way we can enforce that, as we talked about IAM policies to limit who can create subordinate CAs and root CAs. But another one is to use the path constraint. The path constraint, path length constraint is a field of the basic constraints certificate extension. It's used to enforce a CA hierarchy depth. So you can select a template that has a path length constraint of 0, which means there can be 0 CAs below this CA in the trust chain. And ACM Private CA will enforce this. So if you try to issue a subordinate CA from a CA that has a path length of 0, it'll fail. It'll generate an error. But you can also set for each level in your hierarchy a path length of 3, 2, 1, or 0 according to the level. And this is a best practice to basically just security depth, defense in depth, to allow you to restrict the certificates that can be issued at any level in the hierarchy. And really, it gives you additional control over the certificates that can be issued. Another factor to consider is that you really want to use the minimum CA hierarchy height to meet your objectives for delegation of control, administration, and security. And the reason for this is that each CA in the hierarchy increases the number of certificates in the chain, which increases the complexity and time to validate this certificate. The reason this is the case is that the server, TLS server, when a client connects, the server sends the entire certificate chain to the client. And a shorter chain means less processing, computation on the part of the client, and also less network bandwidth to send a shorter chain as opposed to a longer chain. And the objective here is to plan the shortest chain length as possible, but no shorter. So if you need to have delegation or a level in your hierarchy to support delegated subordinates, by all means do that. But if you don't need it, then I would recommend keeping the chain or the CA hierarchy height as short as possible. Another consideration is the CA validity period. And RAM showed a root with a 10-year validity and an issuing CA with 3-year validity period. And question is, how did he come up with those? And what you want to do is really work backwards from the end entity certificates that you issue. And the reason for that is that CAs cannot and should not issue certificates that last longer or have a longer validity period than they do. So ACM Private CA enforces this constraint. And the reason is clients check the certificates chain to make sure each CA in the chain up to the trusted root is not expired before they choose to trust that certificate. If any one of the certificates in the chain, a subordinate CA certificate, for example, has expired, then the client will not trust the end entity certificate because the chain is effectively invalid because the one of the intermediates or subordinates has expired. So ACM Private CA enforces this and won't let you issue certificates that have a longer lifetime than the issuing CA. So the way we want to think about this is to start with, in this diagram, start with the end entity certificate at the bottom. And in our use cases, we want to have a 1-year end entity certificate. Your use case may vary. You can issue certificates as short as you want or as long as you want. In this case, we picked a year. Once we pick a year, we know that for resources that are still around after 9 months, we're going to want to renew those. So we have a renewal cycle that has about a 3-month window. So we renew a 1-year certificate after 9 months, and we repeat that on an ongoing basis. That also means then when we look at the issuing CA, we want to look at the validity period of the end entity certificate as a guideline. So what we typically do is multiply the validity period of the layer below and add some buffer time. So in this case, we multiplied the 1-year expiration or validity period by 2 to get a 2-year period plus some buffer time. That gives you, the buffer time really gives you the time to, if you fail to replace the CA within this window, this buffer time gives you extra time. And so we picked 3 years for this case. And after 2 years, we're going to replace the issuing CA. And effectively, that's every 2 years. But if we don't, we still have a full year before that CA expires. And that's the purpose of the buffer time, is to avoid expiration of an issuing CA. Likewise, for the root CA, we picked 10 years. And this is essentially 2 times the 3-year period of the issuing CA, which gets us to 6 years. And then an even longer buffer time for the root of 4 years. And the reason I picked 4 years for the root for the buffer time is sometimes in the case of the root, it takes longer to distribute the root CA certificate and make sure that it's installed in the trust stores of all of your servers and clients that rely on the trust store. And again, this is just a guideline to show you one example of how to enforce this invariant that the CA validity period has to be longer than the lifetime of the issued certificates. There's a lot of other factors you might consider. Maybe this buffer time is too long for you or not long enough, depending on your operational environment and how long it takes, or how long it might take to upgrade or replace. And finally, operations, some things to consider. RAM showed a manual way to distribute roots to a browser trust store. This is not going to be how you want to distribute roots in your environment. You want to have some automation that's going to either install the new root certificate into trust stores, or to build the trust stores when you're building an image to make sure that your root is installed. And there's lots of ways to do that. It's beyond the scope of this talk today, but if you have a PKI environment today, you're probably have some mechanisms that you're using to distribute root certificates. And next is thinking about revocation and vending status information. You want to, as I talked about before, make sure the CRL bucket, the S3 bucket where the CRL is distributed, is available. You also want to think about when you're revoking certificates, do you want to revoke certificates just because you're not using them anymore, or specifically because you know that the private key has been exposed? And there's pros and cons of how to think about that. More revocations increases the size of your certificate revocation list and can increase the time of the client to process when it's checking the validity of a certificate. And frequently, if you're not, if you unless you know the private key is compromised, you might consider just letting the certificate expire naturally without revoking it. Again, pros and cons to that, but you want to think about what your policy is. And then finally, redundancy and disaster recovery. You want to think about what happens in your environment if your issuing CA is not available. If your environment is going to stop, you want to think about having more than one issuing CA that's accessible. An ACM Private CA has an SLA of 99.9%, but you still want to think about the implications of if it isn't available at the moment that you need it. What is your plan? Are you going to go to another region, an endpoint in another region, or a CA, subordinate CA in a different region? An ACM Private CA is available in 17 regions, so you can certainly have a subordinate CA in a different region as a backup or as a disaster recovery mechanism. You also can think about having multiple routes if you wish. Typically, you would have one route because the availability is not as big of a concern because you're infrequently using that route to issue subordinate CA certificates. But if you're, for example, using your route directly, as the use case I talked about before, then you do want to think about availability and what's your policy for recovery and disaster recovery. That's all I have for today. Thank you for your time and staying with me through this presentation. If you want to reach out to me, my Twitter alias is @ToddSignetti with an underscore, and Ram Ramani is @RRamani. At this time, we have some time for questions.